Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everybody. It is my pleasure to introduce TJ Hazen from MIT CS AI Lab. We met by virtue of the iCampus project. We collaborated with MIT, and TJ has been extremely helpful in giving us some data, and today he's going to talk some more about the iCampus project and the lecture transcription project that they have going on there.
Right. Okay. So since I see so many familiar faces, I know a lot of you already know a lot about this project, but I will go through some of the high-level things about what we have done in the past that you've probably seen, and then also some more recent experiments and some directions that we are hoping to go with it. First off, in terms of who is working on this, there's a long list of students. Jim Glass is heading up the project at MIT, and we have collaboration with Regina Barzilai and a couple of her students. Regina works on segmentation and summarization of, well, previously it had been on text, but now she's branched into working on speech. And then the rest of these people are staff and graduate students that are also working on the project. And of course, the primary sponsor for this project has been the MIT Microsoft iCampus project, which is coming to a close this year. So of course, the motivation for this work is that there's been a large increase in the availability of online academic lecture material. So we have projects like the OpenCourseWare project at MIT. OpenCourseWare at MIT is attempting to put the academic materials for 2,000 MIT courses online and freely available for educational purposes. Most of the time, the academic materials are simply things like the lecture notes and slides, maybe the problem sets and other materials that are distributed to the students. But in some cases, professors have agreed to have their lectures videotaped, and they're provided over OpenCourseWare with streaming video for people who want to watch the videos of the lectures. Unfortunately, when you have something such as the OpenCourseWare project, where you're trying to put all of the material for a particular course online, it typically takes a large human effort if you want to organize it all in some way where it's easily accessible for students. So the goal of our work is to try to figure out ways where we can use speech and language technology to speed up the process of making this material more readily available. So in terms of speech, you'd like to be able to transcribe it, for example, index it, maybe summarize it, find ways that will help students get to the material that they're interested in quickly. So yeah, here are the various things that we're looking at or hope to look at. Some of these things we haven't necessarily looked at yet, but lecture transcription, of course, is the first thing that we've looked at using our speech recognition technology to transcribe the lectures, index them, and do retrieval. We've been working with Regina Barzilai, as I said, on segmentation and summarization of the lectures, and we're hoping to get into the area of automatically aligning these with parallel materials, such as the slides or textbooks. So if someone is looking at maybe a chapter of the textbook and they say, I want to find relevant lecture on this topic, we can automatically direct them to an appropriate lecture on that topic, for example. So I thought I would just play for you a 1-minute clip. This is a sample of one of the lectures, so you get an idea of what it is that we're working with.
I've been multiplying matrices already, but certainly time for me to discuss the rules for matrix multiplication. And the interesting part is the many ways you can do it, and they all give the same answer. And they're all important. So matrix multiplication, and then come inverses. So we mentioned the inverse of a matrix, but there's That's a big deal. Lots to do about inverses and how to find them. Okay, so I'll begin with how to multiply two matrices. First way. Okay, so suppose I have a matrix A multiplying a matrix B and giving me a result, well, I could call it C, A times B. Okay. So let me just review the rule for this entry.
Okay, so what you'll get out of that, first of all, is that speech is not nearly as well behaved as text, so many of the natural language processing techniques that you have might need to be adjusted slightly. Lots of false starts, lots of digressions, maybe from the main theme. So for example, you'll notice the first four sentences here all are introducing matrix multiplication, and then he briefly digresses to some other topic, inverses, because he's going to talk about that later. Then he goes back to matrix multiplication. And if you look at a comparable section of the textbook that covers the same material, what you'll find is that in the textbook, it's much shorter, much more concise, gets right to the point. There's a certain amount of I guess redundancy when people are talking that you don't typically encounter in the textbook. But one thing that you might be able to do is if you're trying to, let's say, transcribe this, if you actually have the textbook available, you might be able to use the textbook to help you figure out what are the proper terms and phrases that are going to be spoken about, do some language model adaptation, for example. You know, and then when somebody comes along and says, I want to learn how to multiply matrices, hopefully you have some organized way where they can access all of this information, the textbook, the lecture, and of course this is the whole challenge, is to figure out how we're going to use the spoken language technology, natural language technology, to organize all this information. All right, to get started, we collected a corpus from MIT. We got we have the audio and video, but we started just by looking at the audio from 8 MIT courses. These are the full semester's worth of courses, plus 80 independent seminars that were given at MIT. These are on a variety of scientific, business, and political science topics, roughly 300 hours. And we had either found text transcripts that were generated prior to us getting started on this project, or we contracted out to get text transcripts for all this material. And we've automatically aligned these transcripts with the audio. Right now, we haven't got all 300 hours yet, but we've got considerably more than 200 hours. I don't know what the exact number is today. And we also have additional materials, such as the lecture slides and the course textbooks for many of these courses. And when we started looking at the lectures, we wanted to figure out exactly where on the spectrum of speech do these lectures fall. And we find that they tend to be much more conversational in nature than, say, broadcast news. Many of the things that we notice in the lectures are more similar to corpora, like the switchboard, the human-human conversations in switchboard, than they are to the prepared texts that you typically are read in broadcast news. So you have lots of filled pauses, partial words, contractions, false starts, etc. All these things are quite common in the lectures that we typically see. Next, we looked at the vocabulary. On average, we'll see on the order of 7,000 words per lecture. The interesting thing, though, is that the number of unique words per lecture is relatively small, typically on the order of 800 on average. And here you see a histogram of the number of unique words in any given lecture. And this is roughly 1/3 the number of unique words that you would have in 1 hour broadcast news. And this is primarily because you're talking about one specific topic and you have one specific speaker who tends to stay within some narrow range of vocabulary. However, even though the vocabulary size tends to be quite small, when you're talking about especially technical lectures, the vocabulary usage tends to contain many words that are not typically used in day-to-day conversation or in broadcast news, for example. So if we look at 3 courses here, and we looked at the vocabulary usage over 3 courses, so we've got computer science here. Here you have, what we did was we took these 3 courses, computer science, physics, and linear algebra, and we removed all of the words that appeared in more than one course. So what we were left with was the words that only appeared in one course, either computer science or physics or linear algebra. We ranked them by occurrence, and so these are the most frequently occurring words that only appear in the computer science lectures, the most frequently occurring ones that only appear in physics and in linear algebra. And then these things here are the ranks of how often these words appear in the broadcast news corpora and in the switchboard corpora. So what you'll find here is that procedure, although very common in computer science, not terribly common in broadcast news, and much less so in switchboard. And then you have some other terms like magnetic, for example, very uncommon. And these dashes here indicate that you've never seen them before. So eigenvalues and orthogonal and matrices never appeared in either broadcast news or switchboard. So if you're trying to predict what words are going to be spoken, you definitely have to have subject-specific material. Cons and could'er are 2 Lisp terms. Okay, so it's not cons like pros and cons.
Okay.
But that's where this is from. This is coming from like the pros and cons.
Great.
Whereas could'er and cons are 2 operations on a structure that has 2 things. Cons is the first element, and could'er is the second element, and it comes from registers that had way back. Yeah.
So if you just done pairwise scatter plots or something of this, you would show this point, larger, and what you probably see is the correlation is just a whole lot better if you're on related subjects than if you're not.
Right. Right. Yeah. We haven't done that specifically, but.
Well, it's well worth doing.
Okay.
But you need to do it on a log paper.
Okay.
And then you need to do something about your zeros.
Oh, okay. You mean these things here?
Yeah.
Okay, so then we're curious about how can we cover these words. And so we looked at a particular set of computer science lectures and what the added vocabulary rate was when we derived the vocabulary we're going to use for the recognizer from a variety of sources. So, for example, if we use the broadcast news corpus going all the way out to all 64,000 words in broadcast news, our added vocabulary rate is still over 1%. I'm not exactly sure what this number is. And this is with 64,000 words. If we go to switchboard, we get a very similar added vocabulary contour here. So just adding the most frequent words in broadcast news or switchboard still leads us a fairly high added vocabulary rate, even with a large number of words. If we look at just lectures in math and physics, so lectures but from a different topic, we get a slightly better curve here in terms of, it's more efficient at picking up the words, but this is only 7,000 words, so we don't get, there's a very large number of added vocabulary words if we only look at the vocabulary from those lectures.
Well, is it surprising that that curve looks so similar to each other across different domains?
It's surprising to you?
Well,
I mean, broadcast news and switchboard are both over a wide variety of topics. So
I thought if you have, specific, computer science course, the behavior, it's just hard to think whether they should be the same.
Well,
maybe everything's.
I think they would only be different if one of them happened to discuss computer science more than the other. But I don't believe either one of them discusses computer science to any great extent.
Okay.
Now, I guess because computer science has an overlap with other engineering fields, you're going to pick up math and science terms in your computer science lectures, which just might be why the math and physics lectures are better. This blue line is now if we just use the textbook. And It starts out quite a bit worse, and this is largely because so many of the conversational terms that we use.
I didn't read it right. So the OV rate is computed based upon a fixed lexicon to begin with.
Yeah, so we vary the, no, well, we have a lexicon.
Yeah, but if the lexicon is generic lexicon, then you go to specific topic. Of course, you expect more
Yes.
OV rate. Is that reflected here?
If you go to a specific topic, well, I'm not comparing other topics. I'm only looking at computer science here.
I see. No, but different colors.
So the different colors are where we're deriving the lexicon from.
I see.
So that's the only place the lexicon is coming from, right?
Right,
When you
right.
see a textbook, it's just from this.
Right, so the blue line here is if we derive the lexicon from the most frequent words in the textbook.
So you're missing out on conversation.
Right, so it's higher, it's worse here because we're missing out on conversational terms. It gets better because it starts picking up all the technical
I
terms.
see.
Okay, but it's only got 5,000 total words in the entire textbook, so we still have a large amount of vocabulary.
So one is 1% or 100%?
This is 1%,
That's 1%, and the one on top is 100%.
100%. Yes,
And the scale is logarithmic.
yes.
Presumably,
Both scales are
we have
logarithmic.
10%.
What's that?
Presumably, in the middle, we have 10%.
Yes, yeah. So yeah, I'm not sure whether this is like 2% here. Roughly 2% would be, I guess.
So you took the lexicon from the textbook material?
Right, well, each of these different lines represents a different source that we derive the lexicon from.
Okay, so you have all the lexicon for a particular subject.
Right, well, I mean, this blue line is the lexicon derived from the most common words in broadcast news. So as we add more and more words from broadcast news based on their frequency in broadcast news, we drive the out of vocabulary down. But it takes 64,000 words, and we're not even at 1% yet.
Now, in text-to-speech, we work for getting vocabularies that were coverage like 4 nines rather than 1 9 or 2 nines.
Right.
Okay. And we could get there, but our vocabularies were, I think there were, hundreds of thousands of words,
Right.
close to millions.
Right.
And I guess, so why don't speech recognizers want to go there?
Well, mostly it's the search time. It's very inefficient to search, do a search over 500,000 words.
And does the search scale linearly with the vocabulary size, or is it sublinear? I mean, how bad?
Well, it's probably sublinearly because if you have, well, depending on your search network, if you have an efficient search network,
You would hope so.
you'll have some sharing on when you're computing the acoustic model.
I mean, what this seems to be is a pretty strong argument. You better, if you want 3 or 4 nines. I mean, 1 9 is just unacceptable, right? I mean,
well, it depends. Yeah, I mean, it depends on what your goal is. If it's 1%, yeah, that might seem unacceptable.
say if I got a 40% word error rate, then what the hell, right? If I get 10%.
Right. And it depends on whether you're looking to cover all the obscure things that a lecturer might say.
But the content of the lecture isn't so obscure, right?
Well, yeah, but sometimes they might go off in a digression that's obscure and start talking about.
Words you were talking about were what mattered.
Right. You want to make sure that you cover the most important, the primary topic terms.
But you had the plot before where you showed how many words are used in a given lecture.
Right.
So that's way, way less than all this.
Yes.
So just covering all the possible lectures is a really big hammer. If you could do some sort of adaptation.
Right. Well, that's where I'm going here.
Right. I'm just trying to say it.
Right.
So say if I had the textbook.
Right. So, but if you have the textbook, of course, that it's more efficient. But the textbook doesn't cover all the things that somebody might say. If you have other lectures, that's even like, so if we took this, in this particular case, we were looking at the OV rate over 10 lectures, and we held out 10 other lectures. And if we use 10 other lectures to predict the next 10.
I got a feeling that, for whatever purpose you want to have, if I want to query, metric multiplication, if OV is not relevant here, those OVs are typically resulting from, those conversational
Yeah, sometimes. But sometimes it might be something like the name of a French mathematician that wasn't mentioned in the
I don't
textbook.
care, right?
It might be okay, yeah.
So in this case, the user doesn't even care whether this things or not. Would it be just reasonable to say that, well, as long as the vocabulary, the words in the textbook are correctly recognized, I'll be happy for the user. I mean, I just want to get the core material.
Well, but let
I don't
me
want to
issue a
listen.
query here, which is, I skipped class. I want to know what the professor said is not in the book that I better cram for.
Okay, so you want to... Oh, you don't want to go that deep, right? Like, you know, the example you gave in the beginning.
Right. Well, I'm not certain because you know, we've been working on the technology, and in December we plan on putting out a full browser that covers a whole bunch of courses, and then we'll actually see what students want to do with it. Okay, so.
I suspect my query is probably more.
So I'll tell you what's most useful after we see what people do with it. But we wanted to get to the point where it was actually something useful for them before we just put it online. This next curve is if you had some previous lectures and the textbook, of course, then you get a much more efficient coverage. Same lecturer? Same, yeah. This was 2 lecturers that alternated lectures. So we are seeing. You know, many of the same conversational terms or, you know, verbal tics that they have will be covered from the previous lectures. But we may not have those lectures available, so we want to know, what's the best way that we can handle, you know, using any relevant textual material. So this curve here, the orange one, is if we take all of our non-CS speech, broadcast news, switchboard, other lectures, and combine it with the textbook. And there's a weighting scheme here that weights the textbook a little bit more than the other sources in order to pick up the technical terms. We can drive it under 10% with about 10,000 word vocabulary. I mean, drive it under 1% with about a 10,000 word vocabulary. So it's certainly important that you include all sorts of conversational material in your training material when you're determining the vocabulary, but you also have to have something like the textbook to get all the specific technical terms if you want to keep the vocabulary small so the search is efficient. The other issue is how well does the language model match up with what the person's actually going to be saying. So we were looking at language model perplexities in this case of how well does the language model give you good predictions on the lecture material. So if we train the language model from broadcast news, in this particular case, all these experiments assume that there's no out of vocabulary. So we throw all the vocabulary from the textbook into the vocabulary to make sure that we get coverage. Then we train up a standard bigram with the SRI language modeling toolkit and find the perplexity on held out data on these held out computer science lectures. And these perplexities are quite high when you're training with broadcast news. You get better perplexity out of just generic human-human conversations. You get even better perplexity from non-CS lectures. The course textbook, even though it has all the technical terms you're interested in, is terrible because of the style difference. Subject-specific lectures, held out lectures, not the ones that we're testing on, give very good perplexity. And if you combine the textbook with the held out lectures, you get here. And this is the perplexity if we're training and testing the language model on the same data. Okay. So it's certainly important that you get some subject-specific material if you want to have good prediction from your language model.
Are subject-specific lectures here by the same lecturer? Or
Yes.
They are.
By the same lecturer.
Huh.
So this is a possibility. If you've been doing data collection for a whole semester and you've got 5 or 10 lectures under your belt, then you can use those for the remainder of the semester, for the remaining 10, 20 lectures, however many you have left.
So are those language models built on the same vocabulary?
Yes, they're all built on the same vocabulary.
How much do you think this is subject and how much do you think this is speaker? So you have some lectures.
That's a good question.
And it could be that, I mean, we clocked it.
Yeah.
I'm not graduate, we clocked some speakers that I think it was 30 ohms per minute.
Yeah.
Right? Yeah.
Unfortunately, what I don't have is the same course taught by different lecturers. Well, actually, we could do it with computer science because this is alternating lectures. So we could split it up in a different way. Instead of saying the first 10 and the next 10, we could split it up by lecture A and lecture B.
You don't have any lecturer teaching two different courses.
We do have a lecturer teaching two different courses.
So now you could ask, what if I use that lecture on one course to test against the other course?
Unfortunately, that one is Physics 1 and Physics 2.
Well, that's not different.
Right. Yeah. Actually, this is a good question. What I could do is look and see how well, lecture A and lecture B predict each other for the computer science course. That would be an interesting thing to look at.
Yeah, I just think it's too ambitious to accommodate the kind of queries that Ken talk about. I mean, this is probably, I think for immediate usable system.
Right.
Your very first example. For those, I think all the vocabulary words in the text will probably just be.
Well, yeah. That's what we hope. Okay. So we're curious about how well we can actually do the recognition. So one of the first things we did was we looked at how well the humans do on this. This is because we have these approximate transcriptions where we sent the data out to a transcription service and we just asked them to give us a rough transcript so that we could save some money. And then we took some of the lectures that we got back and we carefully transcribed it. And this was on lectures that we gave. This analysis is on speech recognition lectures. So because of my familiarity with the lecturers, I believe that I can get a very careful transcription of this data. And it turns out that the rough human transcriptions that we got from the transcription service show a 10%. I say error rate. I really should just say difference. There's a 10% difference.
Right. How much of that goes? What's the variance due to text normalization?
Yeah. Okay. So I can give you estimates, but I don't know the exact numbers because I haven't gone in and done a careful study of exactly what the differences are. But anecdotally, I would say somewhere between half and 75% of it is they're actually correcting things, removing false starts, correcting grammatical mistakes that the
So their transcriptions are easier to read than yours?
Yes. So I'm estimating that somewhere between 50 and 75% of it is they're cleaning up the transcript to make it easier to read.
This is the subcontracted ones you
Yes. Relative to mine, which I transcribed everything. I marked all the false starts and everything.
And those services that are out there are more intended to produce a transcript to read. They're
Yes.
intended to produce research.
Yeah, and they come back with punctuation and speaker changes marked and things like that. So a lot of it is useful. We could look at differences. We could use this data to help train up automatic punctuation, for example.
But those services provide a service that people are willing to pay for, and they're tuned to what people are paying for.
Right, right.
They're not tuned to produce data for us.
Right. But now let me get on with the problem with the service, which is that at least 2.5%, I'm estimating 25% of this are of these human, I call them errors, but it's the differences between what I transcribed carefully and what they got, are actual substitutions, where they transcribe the wrong words. And not for the benefit of the reader or cleaning up the transcript.
Is this where you and the audience knows the topic better than they do?
Yes, exactly. What's that? Oh, right, exactly, right. So let me give you some examples. So misspelled words. Okay. I love this one. Yeah. I envision John McCool with sunglasses. Signal processing is cool.
Well, We probably have some website pages, pictures of him. I suspect we have tools where we could doctor it up and you could add a little icon to it.
So, some of these, we would expect that they don't know Furui or they don't look cool. Tukey.
Oh, Tukey.
The Cooley Tukey algorithm. Okay. Even Eigen might be difficult. Gaussian, I was kind of surprised I didn't know Gaussian. Of course, Kepstrom is something that only single person. But these are the easy ones because a quick spell check finds these for you, and that you can correct these quite quickly. The more difficult ones are things like this. So, yeah, we had one lecture where Fourier was transcribed wrong 18 times. It was spoken 18 times and transcribed wrong 18 times.
The same way?
6 different. Right. The most common one was the full wave transform, which I don't. But Fourier was another one, and once it was transcribed as Fourier. Yeah, the Harrier transform.
What transcribers again? High school student?
No, it's a service.
It's a service.
Oh,
So I don't know who the transcribers were from this particular service. We switched services because we weren't happy because we found that there was another service that hires MIT students to do their transcription.
But those are better.
And well, they're better at doing these terms certainly because they're familiar with a lot of the technical terms. The old prairie probability and the resident frequency and the powerful fricative. Actually, powerful fricative is not too bad of a replacement for palatal, but at least it's descriptive in the same way.
So is it conceivable that the recognizer would get this right? Like you actually recognize Fourier right when the guys transcribe it as
Yeah. No, we'll often get these types of terms right. Okay, and I'll show you some statistics on that. But that's because these types of terms tend to be the most acoustically well-produced terms. And as long as you have a little bit of support for them in the language model, the recognizer tends to get these types of terms correct. Where the biggest difference in the error rate comes from all the other conversational things, where the recognizer falls apart.
And what do these services cost?
They typically cost on the order of $25 to $40 an hour, depending on
So cheap.
what.
That's really cheap.
Well, you get what you pay for.
Yeah, not an hour of the speech that you. An hour of their time.
Okay, now what's an hour?
And
How much does an hour of speech cost?
if you want a very crude rough transcript, it's roughly 3 times. And then if you ask for more and more detail, like speaker changes and occasional time marks, it goes up to 4 to 5 times real time.
Okay.
So we typically found that it was costing us for a 1-hour lecture between $125 and $175 an hour when we asked them to do things like put in time markers every 20 seconds and give a speaker change.
The LDC claims they can do it for 100 hours an hour of speech.
But careful, that's a careful.
Well, I don't know what it is.
Right. Now, one thing that we didn't do, which we know would help, and BBN has told us the same thing, is if we run it through our recognizer first, and do something, make sure that you get the error rates down in the order of 20%, and they edit what you give them, that you can speed the process up.
Could you do it the other way, which is have them do their thing, and then you post-process it?
Yeah. So I've been experimenting with that, and I don't have the numbers here, but we can certainly correct on the order of 30 to 40% of the errors with the things that I've been doing. Unfortunately, most of those errors are things like filling in the words that were left out because they thought it would be, helpful.
Could you highlight in some way these suspicious cases?
Yeah, this is what we're looking at. So we have 2 things that we're looking at. One is, running the recognizer and looking at the differences on the non-common conversational words and seeing where our recognizer hypothesizes something that we get something different out of them. And so we can at least highlight those, but I don't necessarily have good numbers on correcting them automatically yet. But we have another technique, which I'll tell you a little about later, which is looking at consistency across the entire lecture. So like I said, Fourier was spoken 18 times. So if you have this thing spoken 18 times by the same speaker in the same lecture under the same acoustic conditions, you ought to have 18 examples of something that looks very similar. And I'll talk a little bit about how we might be able to use that later. So then the question is, well, the first question might be, well, what's good enough for browsing? Of course, we'd like to be able to provide a text transcript for browsing because it's much quicker for somebody to quickly look at a short segment of text, determine this is relevant or not relevant, than it is for them to have to listen to it. But it has to be readable or comprehensible to them in order for it to be useful. So we want to know, well, what was the, what should we be shooting for? So I just looked up a couple numbers. I looked at court reporters, stenographers for court cases, for example. There's a classification called a certified real-time reporter. And in order to become a certified real-time reporter, they have to get 95% accuracy. I'm not exactly sure how they measure accuracy on these things.
What is that?
Yeah, I don't know what it means, but the average transcription accuracy has to be 95% in order for them to be certified. And so these are the transcripts that then would be turned over to the jurists who are trying to determine a case and they want to go back and review things. Liberated Learning Consortium. Does anybody know about this consortium? It's a group of schools that's looking at real-time transcription for hearing disabled students. The primary university is St. Mary's in Nova Scotia. St. Mary's has been designated it has some special status. I forget the name of the status, but for helping disabled students, they get some funding from the Canadian government, and they've been using this to see whether or not they can improve access for hearing disabled people in the classroom with other hearing, normal hearing people in the classroom. And they were using real-time transcription from ViaScribe, which is a variant of ViaVoice that IBM has developed specifically for this task. And they found that if they could drive the word error rate under 15%, that the students, based on questionnaires that they handed out to the hearing disabled students, 15% was roughly the level where students found that they could comprehend what was being spoken by reading the real-time transcript as it came up on the board. So 15% word error rate, it sounds quite high, but if your goal is to comprehend things as opposed to give a perfect transcription, that seems to be what they shoot for.
This probably depends a lot on whether it's like if it's like a history lesson versus like a highly technical kind of discussion. Because you can imagine if it's like a math lecture, then there are certain sentences where you really have to get every single word.
Oh yeah.
Whereas the gist might be fine.
You take G times B.
Right. Yeah.
Oh wait, did he say D times T?
Right. Exactly.
Yeah, certainly things like that. But of course, if they're writing on the board, things like that, it might help. So just keep this 15%. I just put up there as a reference. So when you see our word error rates, you'll have a reference point.
But nobody's got 15% of real time.
Well, so what happens is when the lecturers at these universities adjust their speaking style, specifically so that when they are talking to a group, it's as if they are dictating to their ViaVoice. And they do the training, and they update their vocabularies and all that. Some of them can consistently get under 15%. Okay.
So if we select for speakers and we train the speaker.
Yeah. But I mean, that's a different problem than what we're looking at. We're looking at people who aren't trying to necessarily make themselves more comprehensible to a computer. Hopefully they're comprehensible to the audience. Sometimes it's not so clear. Okay, so we use the Summit recognizer, segment-based recognizer. I just threw this up there just to let you know that it's not exactly like an HMM, but many of the techniques that we use in our segment-based approach are very similar to an HMM. When we're doing the processing, we take the whole lecture. We initially arbitrarily chunk it into 10 millisecond chunks, run a fast phonetic recognizer in its distributed mode over a bunch of compute servers. Define the speech. This process, when we do it in a distributed mode, we can do the speech detection in less than 2 minutes on an hour, and most of that time is the connecting and loading the models. The speech detection is very fast. We go back, we concatenate the contiguous regions of the speech, and then run that in distributed mode again through our recognizer to get the words, and then we'll index the words for information retrieval purposes. So this is essentially what we're doing in the background. The current language model that we're using, we start off with a baseline set of training data, which is the switchboard corpus and a collection of 135 lectures from varying subjects from MIT. So we've got roughly 4 million words of training data. We select well, we also might have user-supplied data as well. So the user has the option of providing papers, articles, book chapters, lecture abstracts, etc. And in some cases, if we have a rough transcript, we will just forget about doing recognition, and we'll just try to do forced alignment instead if they check off that they have what they're providing is a rough transcript as opposed to some supplemental material. But if we're doing recognition, we start off with a pre-selected vocabulary of about 16,000 words. This is relatively arbitrary. I haven't really experimented with going much larger than this at the moment. We add all the new vocabulary items that we find, construct a new language model with some very basic adaptation. And this is some sample recognition results that we can get with completely speaker-independent recognition. So there's no adaptation going on here at all. This is the ASR word error rates that we get and the out-of-vocabulary word error rates if we do not include any of the subject-specific material that is provided by the lecturer. These all being from MIT. One issue that we have is that we have a lot of different accents that we have to worry about. So we've got
Victor Zhu as Chinese accent.
Yes, I consider Victor Zhu to have a Chinese accent, although his accent is very good. The Canadian accent is Jim Glass, but you would never, most people wouldn't recognize him as being Canadian unless he says very specific words. So, and the American one is me. The Dutch one is Walter Lewin, for anybody who knows Walter Lewin. He's got a fairly severe Dutch accent, but it's very intelligible. It's not difficult to understand. Yeah.
So I was looking at comparing the two columns, the adapted LM and the basic ASR, and it looks like all the improvement comes from reducing the out-of-vocabulary rate.
Yeah, that was the interpretation that I had as well. I don't know if that's the case, because I haven't looked at the errors. Well, I would agree looking at the numbers that appears to be the case, but I just got these numbers last Friday, so I don't have, I produced them specifically for here and for HLT. I haven't actually gone in to see what the differences in the errors are. So it might be that we're correcting some out-of-vocabulary words, and that corrects a lot of the in-vocabulary words surrounding them. That might be part of it.
Usually people quote the 1.5 times the out-of-vocabulary.
Okay.
Right?
Yeah.
So
I mean, certainly
consistent with.
Yeah, I mean, certainly here it's 2%, and we drop 3%, so that works out perfectly with what you just said. Here, we drop 1/10%.
Yeah, it does.
So it doesn't jive there. And here we got a much bigger drop than 1.5 times the drop in the OOV. So, yeah.
Yeah, no, I mean, but it makes sense in the sense that, put up your own slides, you're probably going to sort of read from them.
Yes.
You have a textbook.
Yeah.
There's no.
Yeah. So, yeah, we didn't get much out of the textbook. I think partly because this lecture that I happened to do it on was the introductory lecture, and so a lot of the things that he was talking about were not, delving deep into physics yet. So it was.
Transcript what error includes all errors. So
No. So I throw away all the ums and false starts. Now, it is an error. If you hypothesize a word for a false start, that is included as an insertion error.
it's included in the transcript. Okay.
This is a careful transcript.
I just thought done by group rather than.
Yes. Yeah.
Okay.
But like I said, we made arbitrary decisions. So one thing is, I think the actual effective word error rate is lower than this, okay? Because one thing is that we have not been very careful about distinctions between things like what is and what's, for example. So if the recognizer says what is and the transcript says what's, that might be counted as an error.
Jim get much lower error. Does it have something to do with the fact that he speaks relatively slowly compared to others?
Yeah.
He speaks like Bob Mercer. You know, Mercer was the guy you wanted to always use this.
Right.
That's small.
Yeah, and he also, well, compared with Victor and I, he has a much lower, well, Victor has a much higher words per minute than either Jim or I.
That's an important factor.
Yeah, and Jim has got a much lower insertion rate of filled pauses and false starts than I do, at least on this lecture. This lecture is very controlled, very few filled pauses and false starts. But I suspect that this is word error rate is mostly due to the difference in the accent. And I'll show you because we do some adaptation on this later. But yeah, so we're not anywhere close to that 15% yet. Okay, but I think that we could get there with appropriate adaptation. I'll show you that on this next slide. So here we're just looking at that one physics lecture because this particular lecture we had 2 courses worth of data. So what I did was I took all of the other course that he taught out and used that as adaptation data for the acoustic model. And then so running it on. So he taught a course on classical mechanics and a class on electromagnetics. I took all the electromagnetic lectures for adaptation data and then used it for his classical mechanics talks. And so the first 2 numbers are the numbers you already saw, 46.8 and 45.2. If I held out 38 hours, if I added 38 previous lectures, and I just add it into the acoustic model training data, I'm not even doing map adaptation. I just throw it into the regular training data and retrain with that data included. So it's roughly now 20% of the acoustic model training data is from that speaker. We get a reduction of more than 50% in the error rate. And I'm suspecting that if I actually do something more intelligent with adaptation, some map adaptation or something like that, that this might even go lower. So adapting the language model to the topic by using the textbook from the course does not seem to have a big effect relative to this huge improvement that we get from adapting the acoustic model. Okay.
What about, have you tried taking any of the rough, well not rough, but the approximate transcripts that the people have done and actually used that to help train the language model?
Yes.
Okay.
I mean, it's part. The rough transcripts are part of the language model training data. So.
Oh, okay. So you're right throwing that in.
Yeah.
Okay.
But not necessarily the rough transcripts of this course. So I haven't tried that. I haven't tried that yet.
Okay.
Yeah. Well,
thinking, like,
because if you have a rough transcript, what I've been thinking is I'll use the rough transcript to do an initial forced alignment. Then I will see if I can go back and correct.
I guess I'm thinking of a case where, you're willing to pay the $175 for the first lecture, for the first 2 lectures or something, right?
Oh, right.
From then on, right, you adapt the language models
Yeah.
based on that.
Well, I think that was one approach that we were thinking that we'd be doing. Is that you start off, you pay a high cost in the beginning of the course, but then as the lecture goes on, you start relying on the automatic methods. Okay, so the acoustic model seems to be the important thing that we're missing out on. Although I certainly think if we had better language models, it would help as well. But so here's an example hypothesis from our recognizer. And I don't know, if you look at this, can someone tell me what the person actually tried to say?
Well, it has to do with quantization.
Right, okay, so you know what the topic is, but you're not exactly sure what he's trying to say right here. This is the true transcription. Okay, so, this here is a problem with the acoustic model not respecting the syllable boundary. So, the T in here, it's phonetically the same, but the problem is that it's, up here you would never say but trice.
Well, but it's worse than that. The retroflex is all wrong. I mean, the allophonic variation couldn't possibly work.
Yeah, that's what I'm saying. And it's because the T is on the wrong side of the syllable boundary there. It's in the coda position instead of the initial position where it's going to be retroflexed. So this is if we could build something a little bit better. You know, in the past we've actually built models that respect this allophonic variant so that this type of error wouldn't happen. But we found that it didn't actually improve the overall word error rate, but it made our recognition slower. So we've since reverted back to something where we're just looking at context dependency without knowledge of syllable position. And this is the type of error that you get when you do that. But our recognizer runs a little faster when we do that. Yeah?
So I'm just looking at these errors, and if you want to produce a readable transcript, yeah, I can see how we're in trouble. But if you think of doing indexing and what the queries might be here, it's not that bad.
Yeah. So that's where I'm going next. So this is 35% word error rate on this segment. I mean, we've got 6 substitutions and 1 deletion. But like you said, determining the topic of this segment is easy. The problem is that the full comprehension of the segment is difficult, but that may not be important, especially if all you're trying to do is find a relevant lecture segment that you want to view. So that comes to the next question. What's good enough if you want to do retrieval? So we've taken our same computer science lectures, and this is an old experiment. This is actually one of the first experiments we did. So the recognition is based on a much smaller vocabulary than the 16K I was talking about. See you. And so the recognition numbers you get are actually worse than what we're currently doing. And then we want to evaluate the audio retrieval by looking at how well we identify query terms. And we don't actually have human-generated query terms from students right now. So as a proxy for that, we just grabbed query terms out of the textbook index. So we considered terms that are in the index of the textbook might be things that people would be interested in finding. Of course, one thing is that all these are going to be in vocabulary, because if they're in the textbook, then they're in the vocabulary of our recognizer. So it doesn't account for the possibility that somebody might ask for an out-of-vocabulary term that the lecturer actually did speak, but is not in the vocabulary of the recognizer. But I think that mostly that's not going to be that big of an issue. And then we evaluate how well we're doing on finding roughly 10-second audio segments that contain these keywords that might be the query terms. And the criterion that we're looking at here, the word error rate, the precision of the returned segments, what percentage of segments do we return actually contain that query term. The recall, what percentage of segments that contain the query term do we return, and the F measure. And this is what we get, again, looking at various types of adaptation. But you see, even the best that we do here, 40% word error rate, but the precision of the segments we return is 95%. The recall is almost 90%. So we're roughly finding 9 out of every 10 of the things that the person is looking for, we're finding. So what we basically conclude is that we're going to get good retrieval performance even if the actual recognition itself is not all that good.
So for precision recall, you have to have a notion of a document. Your documents are audio segments.
The document are short audio segments. So these are basically pause-separated segments that are, and we force them to be at least 6 seconds in duration or something like that. And I forget the exact numbers, but on average, they're 10-second audio segments.
So if you aggregate at a bigger level, like if you look longer snippets, the numbers get even better.
Yeah.
Right?
If you're aggregating on some query term that occurs 15 or 20 times in a lecture, you're almost guaranteed to find that lecture. Unless, of course, that term is not the vocabulary of the recognizer. Okay, so for retrieval purposes, we think the recognition is good enough. Okay, a little bit about what we're doing right now. We've set this up as a transcription service for people to use, and we provide tools. And basically what happens is somebody will go about, record their own lecture. In our case, we've been experimenting with this little iRiver device. This is actually marketed as an MP3 player, but it has its own recorder, and it can record up to 17 hours on this device at 16 kilohertz.
So what did you choose then rather than Zen or a couple other, any special property for this?
Cost
is about the same as the others, I think.
Okay. We tried it, and it seemed to work well. That's basically it. It was relatively cheap. This particular device, I believe, is on the order of $150 to $200. I don't remember the price.
You can get it at $50 if you want to go for the smallest one.
Oh, the smaller one, yeah. This one has got 17 hours. There's another one which has only got, I forget the number.
I think the smallest one might be a couple hours.
Right, okay. And they have another one which is double this size, which is more. Double the memory size, not double the physical size.
They have one with a disk as well.
Oh, really? So the person would then record, offload the data, convert it to a format that our server can handle, upload it on our web page, and on the web page they can upload an audio file, and they can upload a bunch of text files, which is the supplemental material. We've got a text cleaning program, which is not so great yet, but we're working on it. That will then extract the relevant terms for the vocabulary and throw that data into the language model as well. We then process that waveform and the documents, run the recognizer, produce an annotation, time-aligned transcription that we email back to the person, and then we also provide for them a tool for indexing into a particular format and a tool for browsing. This is I'll show you this tool in a second. This is an old version of what it looks like. It looks a little bit better now. We're just now at the point where we're ready to open this up to the public so people can start trying it. And what we're hoping is that we will recruit some MIT professors to record their lectures with a device like this and upload it onto our server, and then we'll see how well we're doing. So let me.
Two questions. Do
Yeah.
you have information, because this device is far from perfect.
Yeah.
Do you have information how much the lower sound capturing quality impacts the word error rate? If you basically force the lecturer to wear a closed-top microphone and headset, how much improvement you can get? And the second question is the role of compression. In this case, you compress to MP3, which means losses. So you lose the quality in basically in 2 points. How much this impacts the overall word error rate?
I don't have a definitive answer for either of those questions. Listening to them, there is a slight degradation in the performance. It doesn't sound as good as a microphone like this.
It may have something to do with the fact that the microphone is facing down.
Yeah. Yeah.
So
well, yeah.
They deliberately designed that way because of the voice.
Well, what we did notice is that in lecture settings, one of the problems that this device has is it tends to clip. So I think the internal settings were designed more for conversational speech. And when you have somebody in a setting, especially in a big classroom where they're projecting, it tends to clip. Now we have some tools for, correcting some of this clipping with some approximation methods. But
and this adds one more problem because the microphone points down, which means it captures well the sound from loudspeakers, which is equivalent of increasing the reverberation, which is not speech recognition friendly.
Yeah.
Speaking from some experience, we just recorded the Gale conference by this means.
Okay.
We're about to record an MLP by these means.
Okay.
And we're using a couple of different microphones in parallel so we can compare.
Okay. So, like I said, you probably have more experience with it than we have. I mean, we've noticed the problems, but we've also noticed on several occasions that it does reasonably well.
And the amazing nice thing about it is that device is extremely affordable.
Yeah.
Right. And
it's small.
And not terribly intrusive.
Right. I've experimented with actually putting it in my pocket, and that also seems to work well.
So you face the microphone up?
Well, it's faced to the side, actually, because it sort of rests on its side.
So maybe we should try that as well.
One of the...
It's inside the shirt.
Yeah. The primary reason, though, was because when I had it on my shirt, it would often click against my buttons.
Yeah.
And then you get these clicking sounds.
But it's light enough that you can just clip it on the collar.
Yeah, if you have a little clip. We don't, we'd have to adhere some clip to it that we haven't tried yet.
Yeah, from user the next thing is that you just hang up over there. Everybody become very voluntary.
Right.
They're very happy. They thought it's a kind of like this.
Yeah, it's completely non-obtrusive for the most part. And the other thing is that one other thing that we've been using with these things is just having, we had 6 undergraduate students who agreed to wear these things for a couple weeks during their working hours and leave them on. They could turn them off at any point in time, but we wanted to see, well, how well could we do with just their standard conversations and, you know, recognizing various things. And it's a very, very challenging problem because you've got all the background noise, machine noise or car noise or whatever, plus the fact that most of their conversations are with friends, and there's, you know, it's not like a lecture where the person is trying to project and be very clear about what they're saying. So it's much worse than even switchboard, you know, which, as you all know, is quite challenging. But it does. The device then does tend to pick up everything, so that, you know, as a human listening to it, I have no trouble understanding what they're saying. So, well, I mean, I might have trouble understanding what they're talking about if they're talking about something that I have no knowledge of. But the quality of the audio is not so bad that as a human I have problems with it.
But the sound system in the lecture hall is probably easier for you to listen to than these recordings.
Yes. Well, I mean, it's certainly clearer. I mean, you don't pick up all of that extra background noise that this device
If we measured you on any of the standard psycholinguistic tests, reaction times, or
I'm sure that this would be better, but I can't quantify it. But, you know, this also depends on the lecturer. I mean, if a lecturer is going to go through the trouble of recording their lecture, they might want to have a high-quality one and all that. But it's a matter of cost. For us to have our audio-visual people come in and do a video is fairly expensive. For us to record on this little device, it's pretty cheap.
Can you teach the professors how to turn the device on and off?
Yeah, I mean, we have shown them. Often what we've done is we've had the undergraduate student come in and say, press this button when you start, press it again when you stop, and that's all they need to know.
They can do that.
And they can do that, yeah.
Is this MIT?
No, this device is truly non-intuitive.
Yeah. I mean, no, the interface is terrible. I mean, yeah.
I was spending last night trying to write instructions for the student volunteers. I'm not sure that I succeeded. I'd like to try some people on.
Okay. So let me just give you a quick demo showing you the browser that we set up. And these are the 4 courses that I was able to fit onto my hard drive here. I don't have the full course for all of them, so I only have the 3 lectures that I showed you earlier for this one. Of course, being MIT, we love to refer to things by their number, so just to be kind, I'll give you the actual courses here as well. Of course, people at MIT would never say, oh, how'd you do in your Introductory to Computer Science course? Or actually, it's the Structure and Interpretation of Computer Programs is the official name. They would just say, oh, I got reamed by that 001 exam. And this is what we did in terms of the processing for these, just to show you the range. So for the linear algebra automatic recognition on a previously unseen lecture, for the computer science, we actually had a little less than an hour of each of the 2 speakers giving lectures on a different topic, but largely not much data from those 2. For the physics lectures, we had, well, it turned out to be 30 hours when I went back and looked at it, 38 hours. So more than 30 hours of training data for that lecture. And then just to show you an example of our forced alignment. So for the automatic speech recognition, it's forced alignment from approximate human transcripts. And let me see if I can, oops. Oh, no, I quit out. All right. Yeah, okay. So we can enter some query topic. So for example, you know, I could do something like speaker adaptation. So this will just give you a sense of how we're doing with the forced transcription, automatic alignment. So we're just having the recognizer do the alignment on its own without any time markings over the course of, in this case, these were 90-minute lectures. So it found one lecture, lecture number 19, and it found this term 3 times, this specific term 3 times. And so I'll just go and play this.
Or background noise conditions as well. But I'm going to gear it towards speaker adaptation. So when we're talking about speaker adaptation, one thing that we might want to do is consider how well do we do at speaker-dependent recognition. This is sort of the upper bound on how well you can do for a given recognizer.
Okay, so this is, you see a few errors in there of the human, but you get all the important things are there, and it's completely easy to comprehend.
This is a very good transcription. This is human transcription or machine transcription?
No, human transcription. Human transcription, and then we do alignment and.
It costs you $125 an hour.
Yeah.
Speech.
Yeah. Now I've cleaned it. This is the indexed version. The original version has got punctuation in it as well. So this is we clean it so that our recognizer can do the forced alignment, and I haven't gone back to do the alignment against the original, with all the punctuation and capitalization and stuff in there. Okay, now if we go to something like, let me try. Did I spell that right? Yeah, okay. So now the term acceleration, it was found in 10 lectures from the classical mechanics physics class. And if I just choose one, let's say has quite a few of them, like this one, and then I'll just find one of these segments. Now this is out of the recognizer that has been adapted to this particular speaker. So this is roughly the 20% word error rate that I was quoting before.
When we have gravity, an object is influenced by the gravitational acceleration. And the gravitational acceleration is a constant. And we write often for that gravitational acceleration the letter G. Whether I drop an object, or throw it vertically up, or I throw it vertically down, it's all one-dimensional. It becomes two-dimensional when I throw it at an angle. I keep it one-dimensional.
Okay, so here you have a few errors here and there. This one's probably better than 20%, this specific segment here. But for the most part, very readable.
Oh, yeah. It's amazing enough, all the kind of metadata that people talk about. When you get the audio there, you don't need anything else.
Right.
That punctuation, forget about it.
Yeah.
When you get the audio coming in.
Yeah, so the only thing we did was we put in the little, ellipsis dots here for where the pauses were, and that's all.
Useful, man.
Yeah. Now let me go. I'm trying to remember now what a good term is for the eigenvector.
Eigenvector.
Okay. Well. Okay. All right. So that would be eigenvector would be a good one for the linear algebra.
Was it with or without a space?
That is a good question. I haven't cleaned it up. So sometimes the transcriber gives it without a space. I mean, with a space. So the transcripts themselves might actually have it with the space, but the recognizer has it without a space.
So you don't implement a version like regular expression.
Well, we do. We have a cleaning script that is supposed to do these sorts of things, but something like eigenvector is something that is not necessarily in the cleaning script. We take, we have those regular expressions that they use for NIST, from the switchboard evaluations, for example, that we can use in our cleaning. But
Your thing is the regular expression query language, not in
Cleaning.
all right. Okay, so this one, I'm not sure what the error rate for this lecture is, but I'm guessing it's in the 30% range.
That means no repeated eigenvalue.
Okay, there's an error.
That's the nice case. If my matrix and most matrix, if I do a random matrix in MATLAB and compute its eigenvalue.
So, of course, MATLAB is not in the vocabulary. It wasn't in the textbook, so. All right. But this lecture is also still fairly controlled. For those of you who know Jerry Sussman, you might recognize that his style is a little more difficult. Let me see if I can find, I'm not sure which one is him and which one is Hal Abelson, but I don't know. Let me try this one first.
All right, well, let's, on the action, we're going to start out again.
Hal.
We'll
Hal,
try to evaluate recursive factorial 5. Some environment again, E0 with recursive factorial 5.
Okay. Let me see if I can find one from Jerry, because Jerry is the single speaker that the recognizer has the hardest trouble with.
Well, let's see.
Yeah.
What I've shown you now is how to do a simple iterative process and a simple recursive process. I just want to summarize the design of simple machines for specific applications by showing you a little bit more complicated design, that of a thing that does doublet recursive Fibonacci.
Okay, well, I happen to choose a really good one here, actually, for him. But this, this gives you an idea that even though I'm reporting these really high error rates, a lot of the stuff that we get out is actually fairly readable from the recognizer.
But you said these are human edited, no?
No. Only the automatic speech recognition one was the human one. All the rest of them were from the recognizer. The physics ones were acoustic model adapted. These were not acoustic model adapted, but they're all of them are adapted to the specific. They have the language model material like the textbook or the slides available. Yeah.
So this sort of suggests that average error rate isn't that useful in measure. I mean, I'm wondering if it'd be worth showing some distribution of the error rates over documents or some curves.
Right. So I know that the Liberated Learning Consortium looks at things like the minute-by-minute word error rate. And then what they find is that they'll often have long stretches where the error rate is under 10%. And then they'll have some sections where all of a sudden the error rate goes up to 40, 50, 60%.
100%.
Yeah. And typically what they find is that's where the person is going off on some tangent, getting more conversational, getting excited, talking about, telling a joke, laughing, whatever. Some other things other than very controlled speech. And the 15% average error rate that they get is largely going up to 15% because of these very short segments where the recognizer just completely falls apart. And I think that's the same thing here. I happen to find some good ones here just by chance, but there's some other ones here where the entire thing is wrong. And I think that this is essentially part of the issue. It's not like you're going to get every 3 out of every 20 words is going to be wrong. You're going to have large stretches where it's completely correct, and then you'll have other large stretches where it's practically no words are correct.
So do you rank them here? Because what I found while playing with this, the ones that are hard are usually recognized poorly, so they're at the bottom. So when you browse them, you don't.
Yeah. So I mean, the ranking here is just based on whatever the standard TF-IDF scoring mechanism that the indexer used. I'm not exactly sure what the scoring mechanism was. So yeah, they're not here in order by time. You see the time there: 33 minutes in, 52 minutes in, 3 minutes in. They're in here based on whatever the score is from the indexer. So perhaps you get a better score because you're getting all the terms correct. I'm not really sure. And of course, if the recognizer gets it wrong, it's not going to show up in the list anyway. All right. Let's see if I can actually get back to what it was. No? Oops. This one? Yeah, okay. All right. Just a few more slides on where we're going. So I talked earlier about this idea of consistency. If you have somebody that says the same word multiple times, in the same lecture, same speaker, that they're all going to look somewhat similar. So we have a student who's looking at finding sequences of speech that look similar according to some distance metric. And specifically, it's just a dynamic time warping comparison of audio segments. In fact, I know people here at Microsoft have done this with music, looking for music segments that are the same. Basically took the same approach, looking for word segments that are the same. And there's various ways that you can use this. One is, if you find a whole bunch of segments that are the same, maybe you can jointly recognize over all those segments and discover what the word is more efficiently. So you might be able to get a more consistent recognition of some term over the course of the entire lecture. And another thing is, if you found a term, you might be able to ask, then find other terms that sound similar to it, based on this measure, not based on what the recognizer said. And so the student is able to come up with clusters that look like this, where connections between the nodes represent high similarity between these nodes, and then if you collect all of the clusters that have some sort of interconnectivity, you might consider them all to be either the same word or similar sounding words. And so this is one example that we got from one particular lecture. And so his technique is able to find things, like Egyptians or Egyptian. Here's one where it found abstraction. This is all from a computer science lecture. Procedure or procedures. And right now, we don't have results yet, but we're looking at using these clusters to help go back and correct the recognition output by proposing that the same word is likely to be spoken in multiple places in all these places in the lecture, and replace where something that is completely different than these words with a word from, let's say the majority word, for example. Okay, I'm going to spend 3 slides or 4 slides just talking about Regina Barzilai's work. She and her students are working on automatic segmentation. They have a bunch of measures, such as they have a word occurrence similarity matrix that they can generate. Quite honestly, I forget all the features that they're using in it. But this is the similarity matrix of sentences, broken, pause, separated sentences from a lecture. And dark indicates sentences that are similar to each other in terms of some word occurrence metrics that they use. And these red lines here are manually determined segments where, these are segments where some person has gone through and said they're talking about the same topic from here to here. So this was an hour lecture, and a human went in and said roughly there's, 7? Yeah, 7 primary topics that are discussed in this hour lecture. And the interesting thing here is that these word occurrence matrix, the structure that you get out of that seems to line up fairly well with the manual transcription. So we took this and applied it to some lectures where we actually have, let's say this is one example of a physics lecture, 46 minutes of a physics lecture. And they manually broke it into segments for this site, the Physics Interactive Tutor video. And they basically said this is some set of specific segments, and each segment is given a brief summary so that people know what the segment's about. And then on the OCW site, you can select one of these segments and go in and start watching from the beginning of that segment, for example. So here's a segment on making measurements, and then there's a description here. A measurement is meaningless without knowledge of the uncertainty. And then with their, this is just anecdotal evidence that that their approach works. They have some results that they're working on, and they're hoping to put into a paper, I'm presuming, for next year's HLT. But this is one example of a segmentation that their automatic method came up with. And you see, there's some differences, but it finds 4 of the same segments, roughly the same segments, within 10 seconds. It misses a couple that the manual person got, and it added a few that the manual transcription didn't think were there. And then for each segment, they go through and they can find some automatically determined keywords, find the most relevant keywords based on some measure. And so what you find is these are in order of importance or in order of the score that they get out. Then measurements and uncertainty happen to be two of the things that showed up in the manual one. So they want to be able to take these techniques, and then one of the things that they're proposing to do is generate for a segment some slide, automatically generated slide. Now in this particular case, this is the actual slide from an AI lecture, and this is the words that they spoke while this slide was present. And their goal is to be able to generate something that looks like this based only on this. So they've got something that will generate a generic title and then also generate a bulleted list of topics that are in that segment. Here's some examples of the actual reference titles that were provided by the slides from the lecture, and then their automatically generated titles. And there's some differences in the words that are used, which is why I'm showing this, but you can often see some, that roughly getting the general gist of many of the titles. Okay, last slide. So they evaluate this. One way that they can evaluate whether or not they're doing a good job is just looking at what words they generate. And so they take all the words, let's say, in their title, and they have this bag of words evaluation metric where they say, how often is a word that we say is in the title, is it in the title? And they claim that 80% of their words that they generate are words that are in the title. They find roughly 40% of the actual words in the title, and their F measure is 53%. And then they do a similar thing with the content, and they get very similar numbers out of the content. So these are bulleted items that they generate automatically. This doesn't necessarily say that their title is a good title or a bad title. It just says that they're able to find, some number of words out of what is spoken and put them into their title. And there's some similarity between their title and the actual title that the lecture provided. So this is what we'd like to do, is we'd like to take this and incorporate it into our browser so that when people are going in and looking at a lecture and they say, how many hits do I have for a particular term, they can see which segments they're in, and they can go specifically to a segment based on some keyword or title of what that segment is about. All right. There's lots of other issues. I think I'll stop here, but there's certainly things about what's the best way to display imperfect transcriptions. I know that I've talked with Ciprian about, do you want to just show keywords, or do you want to show confidence scores? Does the punctuation matter or not matter? How do we integrate different media? Is there anything in the video that might be helpful to us? Can we do automatic alignment between the slides that are provided and the audio? But I think I'll stop there. Any questions?
So the comment is that we did a whole bunch of this kind of recording with the iRiver and some other devices at the Gale meeting.
Right.
And they're going to have a stenographer. They also had a stenographer doing it, so you can compare and contrast it. Maybe we could evaluate the stenographer. And then we're hoping to do the same. We're planning to do the same recording at HLT.
Okay.
Although we won't have a stenographer in that case.
Right.
But LDC has offered to spend $100 an hour.
Oh, really?
To do whatever they're going to do, and make this a resource that would be generally available. And in that case, we'll have the PDF of the published papers, and maybe we'll get some slides.
Right. Yeah, we tried to do something similar this summer with LSA summer course that they taught. I forget the name of it. Summer Academy or whatever it was. Summer Institute, right. And we got roughly 50 lectures out of that, and some of them we have slides. slide 4.
So did you have a video recording? The first the example you had, is there any massive amount of video recording?
Yeah, we have video recordings for, well, at least 3 courses. No, 4 courses.
But you're saying audio recording is just a whole lot easier.
Yeah, audio recording is a lot easier because you don't have to bring somebody in to do the actual video shoot. Yeah.
This is sort of a tangent, but if you have course evaluations, it would be sort of interesting then for, if you could take the speech data and the evaluations and come up with some kind of extraction of, what makes a good lecture.
Right.
Or, what's, stylistically, or I don't know, I think that would be sort of another, maybe the professors wouldn't like it. but in some sense, just as a general public speaking technique.
I don't know. It would be interesting to see whether or not filled pauses and things like that actually have any bearing at all on whether or not they like the lecture. Certainly the one lecturer, Walter Lewin, the physics lecturer, very prepared lectures. Going to a lecture of his is more like going to a show. It's, completely scripted, and he has lots of interesting demos. And he is generally regarded as one of the best lecturers at MIT. I don't know that the fact that he has very few filled pauses is one of the reasons why, but.
So ultimately, do you have any vision as to, after all this is done, so MIT will create a resource for them, something to help students?
Well, this is our hope, but we have to find some funding to help build, some sustainable source for putting this, getting this material online and.
The video part, I think, is really useful. Looking at the first video, you don't have to do lectures.
Yeah.
Just the audio, no way.
Right.
The thing you notice is the seats are empty. I don't remember that.
Yeah. Well, it was kind of funny because that particular lecture, I believe, was in 26-100, but that course generally only gets about 100 to 150 people. So they're putting 100, 150 people into a lecture hall that just seats 600 or 700.
C-SPAN where somebody's giving a lecture to an empty audience.
Right.
Well, thank you.
All right, thanks.